How will you generate two standard normal random variables with correlation R if you have a random number generator for standard normal distribution? How would you do it for n-dimensional normal random variables? Let's assume that Z1 and Z2 are two independent standard normal random variables, and X1 and X2 are the required two random variables which we have to generate, standard normal random variables which we have to generate in such a way that their correlation is R. So we take one of the random variables x1 same as z1 and the second one as a linear combination of z1 and z2 in such a way that the correlation between x2 and x1 is R. We can write this correlation as the covariance between x1 and x2 divided by the product of standard deviation, which is the square root of the product of variances between x2 and x1. So now our goal is to find the values for a and b. So first we substitute the value of x2 as az1 plus bz2 in the numerator and also in the denominator here, and then we expand the covariance terms here. So we get a times covariance of z1 and z1 plus b times covariance of z2 and z1. So this will become the variance term of z1, and this would be 0 because the covariance between z1 and z2 is 0. Similarly, we expand the denominator variance terms. We get a square variance of z1 plus b square times variance of z2. So finally we get this term, and then we'll have to substitute the variance of z1 and z2 equal to 1 because it's a standard normal random variable. So substituting the value of variance of z1 and z2 is equal to 1, we get the correlation equal to a divided by square root of a square plus b square. And we also know that the variance of x2 is 1. So putting in the values of x2 as a z1 plus b z2, we get a squared plus b square is equal to 1. Solving the above two equations together, we get a is equal to r and b is under root 1 minus r squared. So the random variables which we are looking for, x1 and x2, is x1 is z and x2 is r times z plus 1 minus r squared times z2. So this is the answer to the first part of the question. For the second part of the question, we need to generate an n-dimensional multivariate normal distribution with the mean mu and covariance matrix which is given to us is sigma. So the first step is to simulate a vector of uncorrelated normal random variables z in n dimension, and then find a matrix C such that C times C transpose is sigma. And once we have C, the required vector which we are looking for is y is equal to mu, which is mean, plus C times the vector z. And to calculate the matrix C, we can either use Cholesky decomposition or singular value decomposition. And to see why this holds true, we can calculate the covariance of the variable y. This is equal to covariance of cz plus mu. Expanding the covariance term, we get C times covariance of Z times C transpose. The covariance of Z is the identity matrix. So we get C times identity times C transpose. This is equal to the covariance matrix sigma. So this is the answer to our second part of the problem.